To see how SYMMIC facilitates thermal analysis of pulse power scenarios, let's work through an example using the generic FET template. Normally, when we compute a steady-state simulation, we're applying constant on power. But for a solution through time, a couple of additional parameters from the heat generation list come into play, and these define a duty cycle of on and off power. For the parameters set here, we have a 33% duty cycle of 75 microseconds. That is, the on power is applied for 25 microseconds, followed by the off power for 50 microseconds. Now I'm going to begin this analysis by running a steady-state simulation with constant on power of 33% of the power that I want to apply in the pulse power analysis. And this solution is going to give me a starting point that's going to help reduce the overall simulation time. The FET model can be thought of as consisting of three main parts: the device on top, the substrate, and the metal shim with its attachment layers. An electrical circuit analogy looks like this. Dissipated power is represented by current, and temperature differences are represented by voltages. In this highly simplified representation, each part can be thought of as having a thermal resistance and capacitance that determine the time constant of the thermal response. The thermal resistance is related to the thermal conductivity and dimensions of the component. The thermal capacitance is related to the heat capacity, mass density, and component volume. So for the particular parameter settings and materials that we have configured in the generic FET template, we see that the device would have a time constant of less than 1 microsecond. The substrate, a time constant between 25 and 100 microseconds, and the metal shim and its attachment layers, a time constant of about 25 milliseconds. Because the time constant of the shim is much greater than the duration of the power pulses, the shim temperature will be the same as a steady-state simulation with a duty cycle times the full on power. So just applying 33% of the full on power and running a steady-state simulation will give us the correct delta T to get the temperature of the shim, and we won't have to run the simulation for a long time to wait for the shim to heat up. Now, one other thing to point out here is that because we're using a large H, the thermal resistance of the film is essentially zero. The 33% steady-state simulation has been completed, so let's save it to a file. Now we're ready to set up our pulse power analysis. So we'll go back to the heat generation list and we'll set the full on power that we want to use. Then we open the simulation times dialog and set up the parameters for the transient analysis. So we switch to a solution through time, and as our starting temperature we're going to use the solution file that we just computed. And this is going to give us the initial temperature of the shim so that we don't have to wait for the shim to heat up. Now what we have to do is fill in this table of step sizes and number of steps to get each output time that we want in the final solution file. Now I could just go in here and type in step sizes in microseconds. That's 1 microsecond for 10 steps, which would give me 10 microseconds of simulation. Or I can use these edit boxes over here. Let's say I want to do 10 cycles. So we have a duty cycle of 75 microseconds. So for 10 cycles that would be 750 microseconds. I want to have a step size of 1 microsecond, and I want to output every step in the final solution. So if I just say fill table, it fills up the table with appropriate entries. So once that's set up, all I have to do is say run simulation. So 3.5 hours later we have this solution, and if I move the time slider at the bottom, you can see I can go through the entire solution and look at the temperature at every microsecond in the solution. Similarly, I can use one of the plots from the results menu to look at the simulation uh, temperatures, the solution temperatures plotted at any time point in time. And so as I go through this max plot, what you can see is that we have these power pulses that heat up the device and substrate, while the shim sort of maintains this constant hot background temperature. So to plot these results, I just go to the recorded values dialog. Now this dialog will have all the values that I asked to be recorded for each time point in the output solution. So in this case, I just have the min and max temperatures over the whole model. So this will give me the peak junction temperatures, and I can just go in and select these rows and hit Control C and copy them, and then I can go into a spreadsheet and paste them in. And this shows the results for the 10 solution cycles. And what you can see, there's a little bit of a transient. We started a little bit hotter than we will in the final cycles, and here it settles down into the final simulation. So if we go back to the SYMMIC window and we look at the simulation times dialog, there's another way we could actually start with a warm shim, and that would be to set a constant temperature. And here we would compute a steady state solution at full on power, and then take 1/3 of the temperature difference between the peak temperature in the solder layer and the backside to get the approximate temperature difference across the shim. Now this is not going to be as good as using the starting solution that had the whole temperature distribution as initial condition, but it should help us get closer to the final solution. So if we were to run that, which I've done, what we find is this. So I ran it for 17 cycles, and here I've plotted the last 7 duty cycles on top of the solution that I showed you earlier. And so you see there's a little bit longer transient, and then it finally settles down to the desired long-term behavior.